Eu acho que... Tudo bem? Tudo bem? Quando você acha que 3 e 5 a gente começa? Não, você que fala. Eu fico lá e você me diz, tá? Tá. Sim, eu vou lá. Okay, hello, good afternoon, everyone. Thank you very much for joining us in this special seminar, special edition, dedicated to the GMT. And we will start with having some words from our director of the Institute, Professor Edmilson Diaz de Freitas. Please, Edmilson.
Hello, everyone. Good afternoon. I received this mission from Professor Claudia to talk a little bit about the telescope, which is not my field of expertise, but actually I participated a little bit of this whole process of GMT when I was working in FAPESP for a while. One of my duties over there was to take care of the whole bench of telescopes. So it's something that I'm a little bit familiar, but it's a great pleasure to welcome the president of GMT to the Institute of Astronomy, Geophysics and Atmospheric Sciences of the University of São Paulo. Today's visit is particularly meaningful for us because our institute has played a central role in Brazil's participation in GMT from the very beginning. In 2014, the institute helped lead the efforts that resulted in FAPESP joining GMT as a founding partner. A strategic decision that positioned Brazil among the leading participants in one of the world's most ambitious scientific and technological projects. Over the past decade, this partnership has transformed our institution. What was once a relatively small instrumentation effort evolved into a consolidated reference center in astronomical instrumentation and advanced technological development. Today, the Institute and its collaborators have strong and growing expertise in optics, mechanics, optomechanics, software, system engineering, control systems, and scientific instrumentation. In fact, Brazilian researchers and engineers became recognized contributors across multiple GMT instrument teams, building long-term technical credibility and internationally respected expertise within the collaboration. Maybe the most important point is that GMT represents much more than astronomy alone. It has become a platform for technological capability building and development of expertise. We are therefore very honored by this visit and deeply grateful for the continued partnership between GMT and the Brazilian scientific community. Welcome to IAG, Professor.
Okay, now following this introduction, Professora Claudia will introduce Daniel Schaff.
It's a great pleasure to have Dan here with us. Dan has become the president of the GMT in 2026, so very recently, and already came to visit us, and it has been very interesting because we also visited FAPESP. So this is really important for us that he's here today. Dr. Dan Jaffe is also a professor at the University of Texas at Austin. And he was, until very recently, the PI of one of the first generation instruments, GMT Nears. So he has also lots to say about instrument building, besides his research in astronomy. So if any of you would like to speak with him, we're going to have a coffee break afterwards, and feel free to join him. So please welcome, and the floor is yours.
Thank you for both of you for those great introductions. I really appreciate it. This is actually a first for me. I may look like I've been around, but actually this is the first time I'm giving a technical talk about the GMT, and I owe a lot to the GMT's chief scientist, Rebecca Bernstein, who created most of the slides, because she's been the astronomical spokesman for the project for many years, and is a wonderful public speaker. So I hope I can do justice to the telescope. It's really a thrilling time to be a part of this project. It's a huge undertaking with really worldwide implications for astronomy over the next 5 decades. If you look at this project, we're going to really be able to push through to do just amazing things that have never been done before. And right now, as you'll see as I talk about it, the project is really moving along in a great way. And we're very optimistic about the future and very excited about the prospects for it. And I hope to share some of that excitement with you as I talk both about the telescope itself, the instruments, a bit about the science, and then a little bit about where we are in terms of the project going forward. So just first of all, the GMTO, the organization that's building the GMT, of which I'm now the president starting in mid-January, is a consortium of 16 astronomical institutions. It's astronomical and science institutions around the world. It's not governments. And these organizations are spread throughout the world, with the heaviest concentration being leading universities and research institutions in the United States. This group has diplomatic standing in Chile. That means we have an official representative there who takes care of our relationships with the Chilean government. And it's using a site that's at Las Campanas Observatory, which is owned by the Carnegie Institution. They're our hosts, and we lease from them. So the site is well established, and as you'll see, it's already partly prepared. So the extremely large telescopes got the endorsement of the Decadal Survey as the premier ground-based project in the 2020 Astro 2020 Decadal Survey from the national survey that was done by the astronomy community, and it alluded to the very important characteristics of the things that we can do with this, both in exoplanet science, in time domain astronomy, in gravitational waves, and in some of the early universe things that we're just starting to discover with the James Webb Space Telescope. The way I like to look at this is that telescopes like LIGO, the Rubin telescope, and James Webb to a certain degree as well, are discovering new things. But with an ELT, where you have many, many times the collecting area, you collect so many more photons, and with instrumentation that can be large and highly multiplexed, we're going to move from this era of discovery to an era of understanding. And that's really the key function of the ELTs as we move forward. So this can come about through a significant improvement in capabilities. The angular resolution of the telescope depends, of course, on the total size of the primary pupil, and so it leads to increases of order of magnitude in resolution over HST and JWST, and the sensitivity scales very, very rapidly with the diameter, and so it can be, depending upon the type of observation you're doing, anywhere between 1 and 2 orders of magnitude more than the current generation of telescopes. And then as you build better instruments over time, you can then produce more effective science by getting higher multiplex advantage or superior performance on a single object. And all of these things are possible with a giant telescope like this. And this telescope is truly gigantic. So here's obviously a rendering, since we don't have the telescope yet. These are the 6.5 meter Magellan telescopes at Las Campanas. And if you've never been to Las Campanas, I brought a comparison that we use with Californians because the reference is clear to them. But since I know that Brazilians are big football fans, this will resonate with you as well. And this is probably a more appropriate comparison. There. So as you can see, this is a very big telescope. So we went through several years ago through what's called a preliminary design, and the preliminary design report went very well and was very complimentary of the GMT and led to this kind of statement about theirs, that it will have the broadest capability of the ELTs and likely the highest performance AO. When you have these broad capabilities, there's a lot of different science you can do, and we'll talk about some of those capabilities and then how it relates to the science as we go along. So here's the telescope. Obviously, if I had it, I'd be done, and we wouldn't be talking. We'd be looking over the data from last night. But this is a very good rendering of what the telescope will look like when it's finished. It's the total wingspan, as it were, the distance across the mirrors is 25 meters. So that just gives you a scale size for this thing. So here are the 7 primary mirrors. Each one is 8.4 meters in diameter. The light comes down, if the animation works. We'll do it the old-fashioned way. The light comes down and then goes up to the secondary mirrors. And those so This is what's called a Gregorian telescope. In a Gregorian telescope, the focus of the individual mirrors is in front of the secondary. The light then expands again to the secondary and is focused down to the main business foci from there. So the light then goes down, comes to a focus at the focal plane, and the instruments are here. So there's a possibility of 2 instruments here that can be switched in and out, and then more instruments here on this rotating platform. So in the case of the instruments here, there are only 2 reflections before the instruments. Here, there's another small mirror here, so there are 3 reflections before you get to the mirror. That's important because the fewer reflections you have, the less light you lose. So the next thing to talk about is the secondary mirrors themselves. The trick here is that each of these secondary mirrors is a mate to one of the primaries. So the light from one primary comes up to one secondary. And that's very important to us in the way the adaptive optics system works. These mirrors are not simple mirrors. They're very complicated devices that include the machinery to make the adaptive optics work. So this is a very thin mirror. It's a mirror that's only a few millimeters thick, and behind it are about 1,000 actuators that use a kind of a piston motion to bend the mirror by small amounts to allow you to flatten the wavefronts with the adaptive optics system. So I'll talk a little bit more about how that works in a minute. So this telescope has a very, very powerful optical design. It has a wide field. It's about 20 arc minutes in diameter with good image quality across the whole field. So the image quality, the intrinsic image quality of the telescope is less than 0.3 arc seconds across the whole field. So for seeing limited observations, you don't lose any resolution across the entire field. It also has a very compact image scale. 1 arc second on the sky corresponds to 1 millimeter to focal plane. And that's an important aspect of it. These adaptive secondaries that I talked about, they're used for several purposes. They provide the fine alignment of the telescope, because as the telescope tips over or shakes, you have to adjust for that in real time. So these mirrors can move in different directions. They provide the phasing. So the telescope itself, in order to function at the diffraction limit, the wavefront that comes from the primary has to be exactly in phase. All of the wavefronts that come off have to be exactly in phase. It's extraordinarily difficult to take an massive 8-meter piece of machinery and move it up and down to adjust on nanometer scales. These secondaries are much, much smaller and much, much lighter, and they can be adjusted then to compensate for any motions in the primary. And then finally, the adaptive optics correction that corrects for the unevenness of the wavefront caused by atmospheric turbulence. And we have about 7,000 actuators, and so that corresponds to about 28 centimeters
each one covers about 28 centimeters in the pupil, and that's about the size of the coherent patch of phase space in normal seeing on a telescope. This whole AO system is a 4th generation AO system. It's been thoroughly vetted by being used on many other telescopes. So this is a robust piece of technology, as fancy as it is. Then finally, the instruments are designed to be moved in and out relatively quickly, less than 15 minutes between instruments. And the instrument suite, as I'll show you in a minute, is quite robust. It's quite generous in its size. Let me go back to this point about the field of view, about the image scale for a second. These are 2 instruments, GMTFs, which is a 2 to 5 micron, a 1 to 5 micron imaging spectrometer, so integral field spectrometer for the GMT, and the equivalent instrument for the ELT. These instruments do the same thing. You'll notice that they differ slightly in size. And this difference is a result of that image scale. That because the image is 1 millimeter per arc second, the size that you need for the instrument is vastly smaller in one case than the other. So this is a comparison of the image scales, and so you can get to the same spectral resolution with a comparable with a 1.5 times smaller piece. And so in general, what this leads to is smaller, simpler, stiffer,
instruments, the possibility of higher spectral resolution. There's more ways to do it, and it's less expensive. So over time, as you look at the lifetime of these telescopes, the flexibility of what we can do with the GMT will be a competitive advantage because of this difference in the optical design, and frankly, of the fact that it's a bit smaller. So here's just a diagram, sort of cutout diagram showing some of the different instruments. So we have instruments running all the way from the UV cutoff in the optical through 5 microns. And so in the optical, there's Gmax, which is a wide field spectrograph that can have a resolution up to about 6,000. And then Gclef, which is an optical shell that's built for precision radial velocity work down to about 10 centimeters per second precision, but also for general high-resolution spectroscopy. And then there's a fiber system called Manifest, which will allow us to utilize the entire 20 arc-minute field by steering large numbers of fibers across this field to allow multiplex spectroscopy across that entire field. And in the infrared, we have 2 instruments, GMT NIRS, which is a high-resolution infrared spectrograph. That's the one that my group has been working on. That has a resolving power between 65,000 and 80,000 and covers the entire spectrum from 1 micron to 5 microns in one exposure. And then an instrument called GMT-IFS, which is this integral field spectrograph that works out to 2.5 microns. The resolving power is up to 10,000. In addition, recently we've added an instrument, GMAG-AOX, which is an exoplanet coronagraph imager, which is designed to flatten the wavefronts with even higher precision to allow for rejection of the host star and to allow for spectroscopy of the exoplanets in reflected light at very high resolution. So one way astronomers like to look at this stuff is to put the instrument suite on a plot that shows spectral resolution along one axis and wavelength on the other. So this is actually not, this is what we call resolving power when you divide the wavelength by the resolution. And so the instruments which get, say, the radio astronomers would say, this is 100,000 is 3 kilometers a second. So that's kind of your velocity resolution, as it were. And then wavelength on the bottom from the optical through the infrared. And here in blue, you see the instrument suite, the first generation instrument suite of the Giant Magellan Telescope. And on the right, you see that for the ELT over here. And you'll notice there's 2 basic differences. One is that that our instrument suite goes out into the optical for much of this work, and theirs also includes a part in the thermal infrared that we have not really covered. So we can put this one on top of the other, and that shows you that difference pretty strongly. So what this means is that the 2 telescopes are complementary, and you'll see this in other ways as well. That's the right way to look at it. The ELT is also building 2nd generation instruments that will cover a bit more of this space. This is another way to look at it, which is to show the field of view against the wavelength. And so you see here that in the field of view space that we have fairly comparable instruments with small fields of view, but we also have with this fiber system a much larger field of view capability. And then again in the single object spectrographs and so on, the capability that ELT has is to work out into the thermal infrared beyond 5 microns that we don't have. So the wide field performance of an instrument depends not just on the collecting area of the telescope. It depends also on the image size. And ground layer AO is the one technique that allows you to make an improvement over the natural sight seeing. And with ground layer AO, you're able to take out over a much larger field than with other AO techniques the turbulence of the atmosphere in the first few hundred meters over the telescope. And that allows you not to get diffraction limited images because there's other turbulence in the atmosphere above that. but to get somewhat better spatial resolution. So here's a plot showing the full width to half max of the image as a function of wavelength. And so the top line, the black line, is natural seeing, where just because the scale size of the turbulence in the atmosphere increases with wavelengths, the size of the images improves as you go to longer wavelengths by a bit. So in a very good seeing site, you might get 600 milliarc seconds at the V band, and out in the K band, you're getting down to around 450. So there's a slow improvement with wavelength. And then as you add this ground layer adaptive optics, you can improve the image sizes. At the center of the field, where the correction is very, very good, you get a very significant improvement. But at the field edge, you're still doing significantly better than you would without it. This translates into significant improvements in your sensitivity. Because if you put a multi-object spectrophoton with a bunch of slits, the amount of light you get through each slit determines your sensitivity. And so when you get the slit to be smaller, when you get the image to be smaller, then you get a lot more light through, and your sensitivity improves. So here you see a curve showing the fraction of light that goes into a 7/10 arcsecond slit, which is the kind of slit you might use, as a function of the full width to half maximum. So when you go from the kind of image you'd have from the natural seeing to what you get with GLAO, you can go from 55% to 85%. That's a huge improvement. That's a 50% improvement in the throughput of the instrument. So that's 50% more photons. That means that a smaller telescope can actually do as well or better than a large telescope if the GLAO works and you're able to do it over this large area. So this is one of the tricks that will help to make the GMT play with the ELT over these kinds of things. The other thing to think about in the sort of competitive realm and the kind of science you want to do is when you're doing particular extragalactic science, when you want a multiplex advantage that's a result of being able to look at many objects at once at similar depth. So in high Z galaxies, for example, where you might have enough in a field to be able to get a multiplex advantage, then the bigger area you cover, the more science you do. And if you have higher spatial resolution, you can see more objects as well. So this is just a comparison of two instruments for the GMT. GMAX by itself, GMAX used with manifest using fibers rather than slits. And there's a vast difference in the area covered in these two cases. The competing ELT instrument is roughly comparable to GMAX by itself with the slits. So you're getting this very significant advantage. And so if you consider if both instruments were using fibers so that they had the same basic sensitivity modulo the collecting area of the telescope per fiber, the advantage as a result of this extra collecting area would be a factor of 5. You'd be able to observe 5 times as many objects per unit time to the same depth. So having that big surface area can make a huge difference. Now, thinking about diffraction limited performance with AO, with natural guide star AO, we'll be able to have a resolution at 1 micron of 8 milliarc seconds. So really, 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 really fine resolution. The STREL, which is the ratio of the amount of light in the diffraction peak to the amount of light that would be in the diffraction peak from a perfect wavefront, is around 75% at the H band at 1.6 microns. That means you're getting almost all the light into the diffraction peak. And that's good in 2 ways. It means more light's coming through your slit, and it means that you're not getting much interference from the light that's still spread over the seeing disk. So you get a much more precise image that way. So here's a comparison, obviously theoretical, of JWST with 32 milliarc seconds, and then the GMT with 8 milliarc seconds. And you see that in a crowded field, you get tremendously better images. You get much more detail than you would have otherwise. This 8 milliarc seconds, if you think about what it corresponds to, it's the equivalent of 30 kilometers at the distance of Jupiter. So you're seeing things that are smaller than the city of Sao Paulo at a distance of 5.5 AU. At the habitable zones of a planet that's 100 parsecs away, you're seeing sizes of 1 AU. And then even in the Virgo cluster, you're looking at a single parsec with that resolution. So you're able to see much finer detail that allows you to start to unpack the physics of different types of objects than you could ever do before. So that's the natural seeing, where you're using the light from the star itself, the light from a natural guide star, from a nearby star, to correct things. The problem with natural guide stars is it's very rare to find a bright star that's right next to the object you want to look at. So often you have to choose the objects because they're near stars, not because they're the objects you want to look at. So you want a way to work on anything you want. And in order to do that, people have developed these techniques of using laser guide stars, where you create an artificial beacon in the sodium layer of the atmosphere at 60 kilometers. You need still a very faint guide star to adjust for the tip-tilt ambiguity of the image that comes down. And using a laser tomography AO, which is the most sophisticated form, you can get areas up to about 20 arc seconds in diameter and do imaging across fields of that size with pretty good STREL, and now with very large sky coverage that's determined by the presence of these guide stars not too far away. So here's an example of how much difference this can make. This is a laser AO image of the galactic center made with the VLT, so with an 8-meter telescope. When you do the same thing, of course, this is a simulation again, with a 20-meter telescope, you get a much sharper image that you'll notice here, the objects you're seeing, and then here, you're now seeing a plethora of other much fainter stars that were not available to you because you couldn't resolve them from the stars around them. This is where you get a gain that's far beyond the gain you get simply from the collecting area of the telescope. You gain very rapidly in crowded fields. This would allow you, for example, in the galactic center, to find objects that are making very close passes to the black hole, that as you follow them, you're able to determine more about the structure of the region around the black hole. So what can you do in the way of follow-up to things that are here? Well, as I mentioned, you want to do spectroscopy. And so you want to be able to take spectra of objects that people find in other ways. So you can compare the sensitivity of the instruments with the GMT. So here, Gmax at 800 nanometers and GMT-IFS at 1600 nanometers to the sensitivity levels for the Roman survey, for the Rubin in its deep surveys, and these are now limits for 5 sigma detections in a 20-hour integration. So they're very, very long exposures. But what they show you is that you're able to go down to very, very deep levels with spectra that then allow you to look at these objects that have been discovered in these surveys and really pull them apart. And this helps with a host of problems of various sorts from that are interesting astrophysically. Another thing that's important to remember is when you're in the southern hemisphere, you have a lot of company. So as we think about the kinds of objects we can look at, we'll be able to take the event sequence from Rubin and follow up the faintest objects that are followable fairly rapidly. It's really important that these telescopes are only 100 kilometers or because they share the same sky. And that means when you get a trigger from Rubin, it means clear over Rubin, so that's what caused the trigger. It's still clear over the GMT when that happens. If you have to go to a telescope in California, for example, it might not be clear there, and so you might not get the answer. You might not get the follow-up you want. But you have all these other observatories capable of observing the same sky and providing you with events and interesting sources to look at. So it's really important to be located where the GMT is located. So let me talk a little bit about some of the science things. You need a number of things when you're starting to do science here. One of them is spatial resolution that lets you separate these objects from each other. Another is broad wavelength coverage that lets you look at different physical phenomena that occur at different wavelengths. And the other is high enough resolution to see what's happening. So the laser's kind of, oh, there, it came back to life. Great. So here you see a number of spectra that were taken at Magellan with Mike of objects at different redshift, from redshift 3, redshift 4.8, and redshift 6. And what you're seeing is the Lyman alpha forest towards this distant object, shifting then to longer and longer wavelengths. And what you also notice is that where here there's just a little bit of so it does die off after a little while. In the lowest spectrum, you see different absorptions from the fact that there's not that much neutral material left by the time you get to Z of 3. Oh, excellent. Thank you. Now I've only got to figure out which button to push, and I'm good.
I think it's this one.
See, I build things, but still I can't make things work. Yeah.
Yep.
And then at Z of 5, you see that the Lyman alpha forest is much deeper, and then at the shorter wavelengths, the neutral material is completely absorbing the spectrum. By the time you get to Z of 6, you're seeing that there's very little space left where there are lines of sight that at that wavelength where radiation can poke through from the original source. If you go to higher spectral resolution, you start to be able to pick this apart, and you can find regions of the spectrum where the transmission is better, and you can start to understand the structure of the neutral material in much more detail. So not only can you go to higher Z here, but you can also start to understand the epoch of reionization much more thoroughly as you get to this ability to see it at higher resolution. Another really interesting area is the area of exoplanets, and Rebecca made this argument, and as a person who's building the other instrument, not this one, I kind of had to get my head around it and decide that I agreed with this argument. When you look at planets that emit their own light have to be either very close to a star, so they're heated repeatedly and come to a high temperature, or they have to be very young, where the energy that's provided by consistent contraction allows them to be quite warm. So Jupiter, for example, which is 5 billion years old, generates about half of the energy of the incident light that hits it. It generates about the same amount of energy as the incident light that hits it by slowly contracting. So it's a little bit warmer than it would be if it were just warmed up by sunlight, but not a lot. But some of the planets around, say, HR 8799 that people detected are quite warm, and that's because they're young and they're still shrinking quickly, and this allows them to be intrinsically warm. But any other planets you want to look at that are colder than that, the only way you're going to get information about their atmospheres is by looking at them in reflected light. So the Earth, for example, if you look at it from a distance, the sunlight hits it, the clouds reflect the sunlight, so you get the imprint of the solar spectrum. But in addition to that, the absorption by water in the atmosphere and by other atmospheric constituents, like oxygen, for example, they imprint themselves in the reflected spectrum. So even though it's reflected light, you see the spectrum of the object itself. So it's very important to be able to do that if you want to understand the chemistry and physics of planets that are not hot or not young. So if you look at the space of planetary radius versus planetary temperature, or this is in Earth radii, 0.1110 on the left, and temperature from 10 to 1,000 degrees, what you'll note, this is all the exoplanets that have ever been found, most of them found by transits. The blue triangles are the solar system, and then these green triangles up here are planets that have been done in either emission spectroscopy or transmission spectroscopy. So what you'll notice is they're all hot. They're all big too, but they're all hot. That's the main thing. So if you want to get into the other regime, you have to have another technique. That technique involves having very high spatial resolution so that you can separate the planet's position from the star, good cancellation of the starlight, and very high spectral resolution. With GMAG-AOX, which is an adaptive optic system that has much finer control than the one that's in the telescope itself, will add to that, be a higher frequency adaptive optic system that will add to coupled with the adaptive optic system of the telescope itself, will provide that kind of capability. And because it works at the shorter wavelengths, it has two advantages. It can see some of these molecular lines that are invisible, but it also actually gets you to higher spatial resolution than you can get with the ELT, because the ELT can't work to quite as short a wavelength. And so it allows you to get at objects that you wouldn't otherwise get at. So here's the same plot now showing the planets that you'll be able to do with GMAG-AOX as well. This allows you to get into the regime all the way down to 1 Earth radius and all the way down to 100 degrees. So it allows you to see Earth-like planets and get their spectra. That's really a revolutionary capability. This is just another way to look at it, looking at planetary mass, going again in terms of Earth masses, and sun equivalence separation. And so if you look at the targets you can do with GMAG-AOX, they go down into this regime where you're down at 1 Earth mass and down at 1 AU. So you can still do objects in that regime as well as other objects. So going back to the original, so this is now in Earth masses and temperature, and you're seeing this same kind of broad capability that overlaps with solar system objects and gets down to kind of Earth and Venus type capability. So it's really finally getting into that regime that's super interesting. Another way to look at this is comparing it to other possible missions. So here you see at the top various missions: the Roman telescope, Habex, which doesn't exist yet, what you get with an 8 to 10 meter telescope, and LUVOIR, which doesn't exist yet, and the ELT, which is a real telescope at this point, not just a virtual one. And these are plots that show contrast on the left and angular separation at the bottom. And so what you see is that, of course, as you get farther from the parent star, you get to much higher contrast. The contrast improves rapidly once you get away, once your inner working angle becomes larger. And you can, with current technologies, you can get down to, at least from space, very low contrast, and with ELT as well because of its very superior spatial resolution. But when you plot what the target and the goal capabilities of GMAG-AOX, they're very competitive in this regime. You can get in very close, and you can get to very, very high contrast. So if this works, it will really provide a revolutionary capability. And it's probably one of the most exciting things that's come along in the last few years. The other lesson from this is when we picked the original first generation instruments, this thing didn't exist. The capability didn't exist. The idea didn't exist. This was added later. And it was added later because the technology had been demonstrated over the last few years at Magellan, and because it was such an exciting capability. The flexibility that's allowed with ground-based telescopes allows it to continue to be competitive or superior to space-based telescopes over time because the technology cycle time is so much smaller. So this is really important when you think about why do stuff from the ground when we can launch stuff now, and SpaceX will just send it up there for us if we send them a check. And the reason is we can build very big telescopes, we can build very complicated instruments, and we can use the latest technology. So this just shows the same kind of plot now, but it is in a slightly different form, which is showing the stellar temperatures for the host stars, the orbital periods of the planets, and who's likely to be in the habitable zone. And again, shows this is now showing for G. Oops, I wanted to go back there. For G-clef here, its ability to measure the orbital periods, and then what's been seen with tests and so on. So I didn't actually study this one too much, so I'm not going to go into this right now. This is a plot now from my own instrument which makes a somewhat different point. This instrument is good for looking at essentially warmer planets and brown dwarfs. And so it covers the entire region from 1 micron to 5 microns in a single exposure at very high resolution. So here we're showing a spectrum with GMT nears this is actually a spectrum at R of 45,000. GMT nears will be even better than that. And plotted on top of it is a spectrum taken with a prism spectrograph at R of 800. Now, JWST is everywhere less than 4,000, so it's kind of intermediate. But what you see is in these cool objects, and this is an 800 degree object, that there's just a wealth of information in the spectrum, and you don't get any of it at the low resolution. You need to go to the high resolution in order to be able to pick apart the physics of objects like this. And that resolution has to be there across the entire band. Just an illustration of this. This is a spectrum of a T6 brown dwarf, so around 1,000 degrees, that was taken with the instrument that we currently have on the telescope, IGRINS. And when the spectrum was compared to models, so here's a model that includes all the usual suspects that are present in these warm atmospheres: CO2, water, CO, water, methane, ammonia, H2S. And when you take these things and you mix them to the right ratios, you can model the spectrum very, very well, almost perfectly. But if you subtract the model from the data, there's an extra line there. That extra line, does anybody know what that line is? That's a line of molecular hydrogen. It's a quadrupole transition of molecular hydrogen. It's the one that shows up in all the shocks that you see in the interstellar space. That line of molecular hydrogen is coming from the atmosphere of this brown dwarf. What that tells you, I mean, you expect molecular hydrogen to be in the atmosphere. That's no surprise. What it tells you is there's no dust. Because if there were dust, this line couldn't be formed. Because it's a quadrupole line, it needs a long column density to be able to be there. And if you had dust there, the continuum absorption would destroy the line absorption. So the presence of this line tells you something about the mixture of dust, that the dust has settled out in this atmosphere. So you get important physics out of it, even though it's not the line itself that's giving it to you. So it's really curious. This is an observation with the same R of 45,000 spectrograph that illustrates the kinds of things you can do in this high resolution regime. So these are observations of an exoplanet not transiting that's observed multiple times at different phases of its orbit. You then cross-correlate the spectrum with templates with different atmospheric constituents, and those cross-correlations plotted as a function of the orbital velocity on one axis and just rest frame velocity on the other tell you the orbital velocity of the planet. So you already have a two-line binary system that allows you to figure out directly the mass of the planet, even if you don't know sign I. And also tells you what molecules are present. So you see in this a detection of water, OH, CO, because you get a correlation peak for all three molecules. And you're able then to infer things about the atmosphere. And with more signal to noise, you can actually measure the shape of the line, so you can get the lapse rate of the different molecules in the atmosphere. You can start to really do atmospheric physics in these hot Jupiter-like planets. This is all made possible by a technology that we developed in our lab at UT Austin. This is what's called an immersion grating. So in a normal spectrograph, as you see on the left, the light hits the, I'm going to make this work. Yes. The light comes from the left, hits the grating, is dispersed by the grating, and comes back off of it again. In an immersion grating, the light enters the material, squeezes down to a wavelength that's 1 over n, where n is a refractive index smaller, hits the grating and it's dispersed and comes back out again. This phenomenon was described by Fraunhofer over 200 years ago. But the technical ability to make grooves in a material like this with enough precision has only existed in the last decade. If you write down the grating equation now, and Fraunhofer did this, I read the paper from 1821, it was very interesting to go back to the transactions of the the Bavarian Philosophical Society of 1821 and read this, you'll notice this n in all the equations that you know about dispersion, the grading equation, and the maximum resolving power. And everything improves by a factor of n. And n in silicon is 3.4. This means you can build an instrument that is that much more capable in a much smaller space. That enabled us then to design a spectrograph, and this is GMT NIRS, that's only 1.6 meters in diameter. It's only about yay big, that covers the entire spectrum from 1 micron out to 5.5 microns at very high resolution and sees all the wavelengths at once, which gives you enormous capability to unlock the physics of disks, the physics of exoplanets, and other types of objects in great detail. So this whole instrument is cooled down to very low temperatures, and it has a series of these immersion gratings, each of which looks at a different infrared band, and there's an infrared detector behind each one. So Ignaz Snellen at Leiden University wrote a review paper a few years ago in which he kind of talked about how efficient different spectrographs are at detecting exoplanets. And the detection speed that this figure gamma that he came up with is proportional to d squared of the telescope, the amount of time you observe, the amount of wavelength you span, and the resolving power. So this is a rough scaling. But we decided to put GMT NIRS on that scaling to see how competitive we were. And what you see is that GMT NIRS is competitive with a second generation ELT instrument, Andes, which hasn't yet been built. Is just sort of in its early stages. And compared to the current instruments that exist, it's an order of magnitude better. So we're already doing this pretty well, but we'll be able to do many more objects, somewhat cooler objects, and detect more molecules, even detect isotopes, which help you to understand the atmospheric chemistry, the origin of the atmospheres, and things like that. So this is going to be very exciting as we move forward. In the high Z case, you can look at what the capabilities of the ELTs will be and what difference that makes. So here's a simulation of a high Z galaxy here on the left. This is that simulation observed 30 hours with JWST, 30 hours with Gemini, and an hour with the GMT. And you can see already in an hour just how much more detail we're getting in the observations because of that strong collecting area. But not only are we taking images, but we're taking spectra at the same time. So that if you look at the individual emission lines, so these are emission line galaxies that are now shifted to very long wavelengths, so that these the typical lines you would see in the optical, like H alpha and silicon 2, and even oxygen 3 and H beta, are coming out in the infrared. And so you can then actually observe these lines, and you can see the kinematics of the galaxy in the line emission at big distances. This helps you understand whether these are actually rotating disks you're seeing with star-forming regions in them, or whether they're more disorganized structures. And that allows you to start to understand about the real formation of massive galaxies in the early universe in a way that's only beginning to be done now. And then there's also this issue, as we now know, about the rapid formation of black holes in the early universe and trying to understand that. And so what can we do that we can't do before? So these are the kind of questions people are asking about where black holes are coming from. How do they form so efficiently? How do they grow so rapidly? What are the supermassive black holes? Do they form before the stellar populations, and how do they connect with the AGN that we see at lower redshift? And if you plot the size of a black hole Schwarzschild radius as a function of redshift because of relativistic effects, they kind of bottom out at a certain redshift. And the angular size doesn't shrink anymore, and so you can then plot on a plot as a function of z what your ability to see things down. This is just illustrative down to the sort of sphere of influence of the black hole. So where it's dominating the kinematics of the region around it. And so with GMT, we can get down to pretty low pretty low radius of J. As you go into visible with adaptive optics, we'll be able to go even lower. This is probably the one area where it's very clear the ELT will have an advantage, because the superior angular size allows you to get to smaller angular distances. But it'll still be an important part of our science because of the instrumentation that we have. So let me talk a little bit about the status of the project at this point, and tell you a little bit about where we are and what's going on. So here you see sort of the major component, some of the major components on the mountain, the enclosure here, the summit support building, which is here, the utility building, and some of the other things that are there. This is what it will look like on the site from a distance. Here you see the outbuildings, the dormitory, and some of the machine shops and things like that. Here you see that support building line next to it. Here's what it actually looks like now. So the dormitory and some of the other support buildings are already in place. The site has been leveled. So you see the Magellan telescopes in the background here. The ocean is over that way. The Sierra is this way. And the water tanks are there. The electricity is there. The internet is there. The site has been excavated and leveled and is ready for the start of laying the foundation. So here's a blow-up of the site. It's really interesting. So here you see the sort of outer diameter of the azimuth ring of the telescope. The pier goes onto this inner piece of rock. This all had to be dug out with hammers, with steam hammers, but hammers. Because if you use dynamite, you crack the rock, and if you crack the rock, you can't put the pillar down on it. So it was very difficult to do this. This is not a trivial exercise to excavate this much rock without using blasting. So it's really quite a feat. Here's what it looks like at night, and just shows you how close you are to the Milky Way. It's really quite remarkable. This is where now a cutaway showing where the telescope will go and what will go on inside this absolutely enormous enclosure. And you can see the Jeep in the background for scale size. I mean, it's really, and there's actually a little person there. So, and then I want to tell you a little bit about each of these aspects of things, just sort of where we are now. So first of all, this is the test bed for the secondary mirrors. This is not the actual full-size operation. And the mirrors are actually made in an interesting way. Is you make a full-size, full-thickness mirror like this, and then you grind away all the glass, so that what you're left with is a mirror that's only a few millimeters thick. That's what makes it flexible. So it's the right shape because it started out the right shape, and you've ground away all the underlying material to leave you with this bendable mirror. Process has been worked out. A lot of the testing has been done on this test bed. The primary mirrors, you might ask, why is this person standing on our mirror? Well, it hasn't been polished yet, so it's okay. But you see the honeycombs in the back. That's the light weighting that's done by using ceramic honeycombs that are inserted before the glass is poured. The glass is actually made, I don't know if you've ever seen this, by putting chunks of glass down inside of an oven, closing the lid, heating the oven to 1200 C while spinning it. And the spinning then causes a meniscus to happen that gives the initial form to the mirror. That means you don't have to cut out as much glass, which would introduce a lot of stress. So this is the initial process, and then you wind up with a bunch of mirrors. We've cast all 7 mirrors for the telescope. We're planning to cast a spare. We haven't done that yet. 3 of the mirrors are completely finished and are in storage now. The fourth mirror is being fine polished now. The 5th mirror is having having the rough shaping of the outside, and then the 6th and 7th have had the ceramic removed from them and are awaiting processing. There's only one machine for doing all the work, so it takes some time. The instruments. No, sorry. This is now the mount. The lower part of the mount, the track that the instrument spins an azimuth on, is under construction in Illinois. This is the factory in which they're assembling and testing the parts. So it comes apart in pieces because you build it all in Illinois and then you have to ship it to Chile, and you can't ship a 25-meter diameter solid piece of steel in one go. And so it's made in pieces. These pieces have to fit together perfectly because as the oil bearing moves around that holds up the telescope, it can't have any bumps in it or the objects jump on the sky. So this has to be perfect to within a few hundred microns on this 30-meter scale thing. So they have enormous milling machines. There's an enormous amount of precision that goes into making this very large object. So it really pushes the envelope on precision machining on large scales. And this company in Illinois has been working on this for quite some time to have it. Here's a piece of the track coming down. You can see they're complicated structures. These are not simply pieces of dumb steel that are going into this thing. And then finally, the instruments. This is a mock-up of GCLEF, the precision radial velocity and optical high-resolution spectrograph. This is sort of a cutaway of the inside of it, where you can see the grating at the bottom here, and you can see the cameras up here. It's a pretty big gadget. So here's some of these are actual photographs of one of the short wavelength camera as finished. So there's a series of lenses in here that image the light onto the detector. Here's the cryostat seen from the outside. This thing has to be maintained at a very, very precise temperature or to have the stability that's needed to be able to get precisions down to 10 centimeters a second. Here's the grating, which is a composite of several large ruled gratings that are shell gratings that are then illuminated from the outside. So these are real pieces in production. GMAG AOX has been prototyped as an instrument at Magellan, and that's what demonstration led it to be selected. And it's a complicated beast, as you can see here. They've got a lot of moving parts to make this very high precision coronagraph actually function effectively to allow us to do this work on reflected light from planets around other stars. That instrument will have its own position, and here some of the fore optics being shown, and then the instrument is inside this cryostat that you see here. This is an image of a test bed for the adaptive optics system for the telescope. This is in Pasadena. We're doing actual tests today of that system using both the hardware and the software to show that if we deflect the mirror, we can correct for it in real time. So that's ongoing. That's a demonstration project that's prototyping this key element of the system. Each mirror needs to be held up. The mirrors are fairly thin for their size, and so when you tip them over, if you left them alone, they would fold over and they might even crack because they're so big. So you have to have a gadget that supports them properly, stresses them so that they keep their form very precisely, but also when a big earthquake comes, can protect them from damaging themselves or each other. So this is now a full-scale prototype, so a 10-meter diameter underlying structure that contains hundreds of actuators that do this stressing, and then you see these large piston-like things. These are part of a hexapod that supports the whole mirror structure that allows it to turn slightly, to bend back and forth at a big thing, and to translate a little bit. That's there both for earthquake protection and for the global motions. And then this is just showing for the dome. We haven't built the dome yet, but we've done very sophisticated hydrostatic flow analysis, hydrodynamic flow analysis to show how air flows through it. That helped with the design to minimize the turbulence that's due to the air flowing through the structure. So where are we? The instrument is, the whole project's now in what's called a final design review. About half the money will come from the U.S. National Science Foundation. They have a very formal process that they use. The telescope was put into this process last June. The final design review will be in the summer of 27, and next summer, northern summer, so June, July, and that will lead to construction funding from the federal government in the federal fiscal year 28, which starts in October of 2028. Construction is actually underway. You've seen many of the parts yourselves. We've raised about $1 billion in U.S. dollars so far. We need to raise about another $300 million to complete the private side of the project, and then the federal government will provide the other 50%. So that's kind of the story of where we are now and where we have to go. It's a really exciting time to be involved in a project that's just going to do amazing things for astronomy and for the whole human understanding of the universe. So thank you very much, and I'd be happy to answer any questions.
Thank you very much for this great talk. So let's open for questions.
First of all, thank you for your presentation. It was really inspiring, and I would like to ask you about the capabilities you showed us. You have a lot of prototypes, and I would like to ask if in the future any of these capabilities could be used in other telescopes, or they are being suited specifically for GMT?
That's a great question. So the question is any of this work, the technical work that's being done, translatable to other telescopes? And the answer is absolutely. So some of the innovations that are happening in the AO space, for example, provide lessons that other telescopes can take on. The precision AO is already being used on the smaller telescopes as kind of prototyping for us, but then as we learn more, that can flow to other telescopes as well. And you know, a lot of the technology for the instruments as we do it is more universal and can be available elsewhere. Anytime you build an instrument for a diffraction limited system, an AO system, that's easily movable from one place to another. So I think in many cases we're benefiting from the knowledge that came before us, and the knowledge that we create here can also benefit astronomers on other telescopes as well. From the science perspective, it drives new ways of modeling the data, it drives new ways of analyzing the data, and again, some of that kind of analysis that gets done by the really big teams that we have through this consortium will be universal, will be applicable to results from other ground and space-based telescopes. That's a great question.
Thank you.
So it's just like a classroom that I ever went to. Everybody sits in the back.
Yes. Dan, thanks a lot for this very nice talk. I would like to ask about when GCLEF and GMT NIRS will be put in Magellan Telescope. Will the rest of the community and also Brazil be able to use this instrument on Magellan, or this has not been decided yet?
This has not been decided yet, and it hasn't even been decided whether we who built the instruments get to use them on the telescope. So this is still a little bit up in the air. My hope would be yes. Let me just explain. So these two instruments, GCLEF, which is a natural seeing instrument anyway, and GMT NIRS, which will be an AO instrument at GMT, but can work pretty well as a natural seeing instrument at Magellan because it's a 6.5 meter diameter. The idea is to put them on the Magellan 6.5 meter telescopes pretty soon. So I don't know the schedule for GCLEF, but for GMT NIRS, it's 2029 is our goal to put it on the telescope in only 3 more years. And the idea is we put the instrument on the telescope, we use it to do the kind of science you can do with a smaller telescope. And for high resolution spectroscopy, you're limited pretty quickly by your ability to analyze the data. You have to have models that include the oscillator strengths of all the lines you're looking at. You have to know the wavelengths of everything exactly. You have to have radiative transfer models. You have to be developing forward modeling techniques. You have all kinds of tools to develop. And so typically, if you put a new high-resolution spectrograph on, the data come out very, very slowly because all these tools have to be developed after the fact. By putting it here, that pain will come during the Magellan time. We'll have a robust set of tools already, a community of people whose science is dependent on this instrument ready. And when we go to the GMT, when the adaptive optics system is ready on the GMT, we will have had 4 or 5 years to really wring out all the problems of the instrument, build a community around it, start to understand what it's best for in the science, and this will allow it to be much more effective on the telescope. The same kind of philosophy is there behind GCLEF, where systematics are going to be what drives your ability to get very precise radial velocities, understanding stellar variability, understanding instrument variation seasonally. These are going to be the kind of things that you'll learn at Magellan that will then translate into observations there. What I will say, Claudia, is these instruments take data that is used well beyond whatever the intended use for. So let's just suppose for a second we do a survey of young stellar objects with GMT-NIRS. We'll make the data public within a year or so, and there's going to be so much in it that the groups can start to practice on it, use it for real science, even if they didn't get the time in the beginning. So I'm not at all concerned about whether other people will be able to precipitate. By the way, any of you who are interested in high-resolution infrared spectroscopy, IGRINS, the instrument we have now, which does all of H and all of K, so from 1.4 to 2.5 microns in a single exposure at 45,000 resolution, all the data up to a year ago are online in reduced form, and you can have access to them. It's the archive is called RIRISA, R-R-I-S-A. You can get at the data. People are using it now without asking. I mean, because we just gave permission. So you can get practice on high-resolution spectroscopy right now with data that's there. Much of it has not been used for anything yet.
Okay, we have a question on the Google Meet, right? Betty, would you like to ask your question?
Can you hear me?
Yes.
Oh,
we
hi.
can see you.
Very, very clarifying talk. Thanks. I have a question regarding comparisons between GMT and other instruments like ELT and in other wavelengths as well. So since GMT and ELT will each excel with different technical strength. So for instance, given that ELT will have a greater light collecting power and angular resolution for extremely faint and distant targets, while GMT will have other advantages like strong adaptive optics and better sensitivity in ultraviolet. My question is, do you envision eventual joint strategies for coordinate programs to, to improve scientific return? And also with regard to other wavelengths, instruments in other wavelengths, do you plan to have synergies with, instruments like gamma rays and gravitational waves? So what is the general strategy on this?
Well, let me answer the second question first. The answer is obviously, as we learn about important astrophysical phenomena, that in particular time-dependent ones, like gamma ray bursts or gravitational wave events, we're going to have a strategy for moving quickly to react. And the ability to, that's governed by two things. One is the ability to see faint objects, which any of these large telescopes have. And the other is the ability to have the right instrument in place at the right time. And so that's one of the things that's driving this requirement that the instruments be switchable in less than 15 minutes, is the ability, is sort of thought through from the gamma ray burst example. So yes, we're obviously going to target things that happen at other wavelengths, fast radio bursts, gamma ray bursts, other types of events that could be interesting. And because we can go fainter than the 8-meter telescopes, there will be new classes of objects to discover. So there'll be new things that we find, and it's very exciting. We don't quite know what they'll be. To your question about optimization, I would say it's complicated because it's a bit of a moving target, because over the next 15 years, different capabilities will appear every year or two at each telescope. So the balance of who's good at what will change over time. The second layer of that question is individual astronomers will find a way to use the best capability for what they want to do. So if you have a compelling science case, if you don't have access to the instrument yourself, you're going to be finding partners at an institution where somebody does. And so if ELT is better at something and GMT is better at another, you'll figure out a way to get it done. So that's the sort of the second layer of that. Then, formal time trading arrangements can be made, and I think the partners will have to figure out what that looks like. or building consortia that go across the two telescopes. I mean, these telescopes are, for the size of the astronomy community in the world at this point, this is only 2 telescopes. We have 16 8-meter telescopes. This time is going to be much harder to come by, and the instruments are going to be more capable and generate more data. So I think on the one hand, we'll probably tend to build larger consortia that build key projects as a mode. And then on the other, there will be such large amounts of very sophisticated data that after a period of maybe 4 or 5 years, we'll be in this regime where we're limited more by the brain power, by the ability to analyze the results, than the ability to collect new data. So I think it's a kind of an interesting science, technology, sociology question. Like, how do you arrange, the human arrangement, which things have more capability, and what science is important? And those 3 poles are interrelate with each other in various ways. And so I think we can solve this problem both with building new capabilities, with thinking of new social arrangements by which we take data, and then thinking carefully about how to get the most science of what we have. So it's going to be very fluid. We haven't really, that's kind of next. First, we have to build a telescope that works. Then we'll worry about that. But I do think there's many ways to think about this. And I think, yes, given how precious these telescopes are, we'll find a way to optimize.
Okay. Thank you very much for your very clear and complete question.
Okay. Do we have another question for Daniel? No? Okay. Let's thank him again. Thank you very much. Of course, we will have time to discuss during the coffee break. And now I'm going to present Professor Alex Karcioff, who is going to talk about Brazilian science in the area of the GMT.
Let me give you the microphone. Thank you.
Thank you for coming.
Thank you.
Mas não está projetando.
Ele me falou que se tiramos este, ele automaticamente tira este daqui.
Isso?
Isso.
Ah, sim. Hello? Is it working? Yes. Okay, so good afternoon, everyone. I'd like to thank you very much for your very nice talk, and also for the invitation that Claudia made me last week to talk a little bit about Brazilian science in the era of GMT. So I tried to put together a talk where we can show more or less the size of our community and what you have available at the moment, and what, of course, GMT is going to provide as new capabilities for us. I think I want to get out. There is something strange here, which is this. I know, but yeah, there is a thing in the corner here, which I don't know how to get rid of. Anyway, so Brazil has a nice position. Like Brazil, only in South America, only Brazil and Chile at the moment have access to 4 and 8 meters meter-sized facilities. So Brazil, for instance, has time at SOAR, which is a powerhouse here for our community. We have about 34% of the time at the moment. Yeah, this is actually acting here. So I'm not trying to use this because it's not working very well. Just a moment. Okay, he's trying to get rid of the thing. So let's see if he gets rid of the thing. Okay. So, oh, okay. Let's give the guy a little time. All right. Okay. Thank you. Yes. So we have then For targeted observations, we have SOAR, which is a 4-meter telescope, 34% of the time. We have access to the 2 Gemini telescope at 6.5% of the time. And in the future, we are going to have time to access to 3 to 4% of the time of GMT. So this is still open as there are things involved here. We also have time access to survey telescopes. So there are several examples. I'm just mentioning a few here. One of them is LSST. Through FAPESP, we have now access, data access of LSST, which is very, very important, of course. We have this 80 centimeter telescope, T8 South, which is open to our community, and we have an important survey going on. I'm going to talk about it next slide. And in the future, we may have like a 150 centimeter telescope for robotic operations too. So here are the main telescopes that I just talked about for the SOAR 4-meter telescope, Gemini, and of course I didn't mention, but I should mention the Pico dos Dias Observatory, where we have like many observatories of smaller size. And this observatory has been operating since the 80s, so 50 years now, and has profoundly changed our community and has been very, very important. For survey telescopes, we have T80. The T80 is the first one here, this telescope here, which is conducting a very important survey with a broad participation of the Brazilian community, which is called S+. And of course, everybody has seen these images already in the previous presentation. This is the Vera Rubin Telescope Observatory, and the LSST. We have now access through a cooperation with FAPESP. This slide very much, because the question is, why do you want to build big telescopes? And of course, this has been very well answered in the previous talk. Why do you need a large telescope like the GMT? And of course, Brazil wanted to be part of it. And since 2010, more or less, FAPESP has put into action lots of efforts to make this happen. So, under the leadership of Professor John Steiner, the late Professor John Steiner, we are now part of GMT. We have a share. We have invested $50 million on GMT. Initially, it was 40 million in 2014, and then it was increased to by 10 million, totaling 50 million, right? But FAPESP, I think it's nice to mention that FAPESP has focused on many other things, not only GMT. We have, for instance, large-scale projects. For instance, CTA, that's who's led. The Brazilian participation is led by Professor Elizabeth, who was the last one to make a question here. We have Mosaic, led by Professor Beatriz in this institute, Llama, which is a radio telescope, and many others. Okay, so there has been large effort by FAPESP to create also a collaboration between academia and the industry with very good results. And instrumentation, for instance, since the onset of GMT, GMT has allowed, with the money that came with it, the beginning of important instrumentation efforts here in our institutes and in other places too. Let's talk a little bit about the size of the Brazilian community. This is, I took from the website of the Brazilian Astronomical Society. We have 362 astronomers plus PhD. I think this is a lower figure because many people are not part of the SAB, unfortunately. But we have a large number of master and undergrad students, and this number of the number of Brazilian astronomers is growing fast. It's very nice to see that we also have a very large and important community of amateurs. We have 124 amateurs registered at SABI, providing all sorts of very important services to the community. And here is a plot showing the number of Brazilian publications in peer-reviewed magazines, right, journals, featuring at least one Brazilian, and this number has increased to a very large number, like close to 600 in the last years. now let's talk about the kind of the profile of the Brazilian scientists, right? About 80% of the Brazilian astronomers are observational astronomers, like I think everywhere else. So this creates high demand for world-class facilities. And this community made of 80% of observers have intense, very extensive international experience. So we have been working with SOAR for 30 years, Gemini 30 years, and many others, AGST, CFG, CFHT, ESO, etc. Right? 70% of the proposals at SOAR and Gemini request spectroscopy. And I'm mentioning this because you've seen in the last talk how important the spectrographs of GMT is going to be, GCLEF, GMAX, and the spectrographs in the infrared. So there is going to be a high demand for, of these instruments for our community, right? And here you can see how this is true when you take the Brazilian papers and you see the kind of a technique that the paper is using. You see that nearly 60% of the papers published in Brazil uses spectroscopy. I put here polarimetry because I like polarimetry and also show that our community has, even though it's like not a very large, important technique like worldwide, because it's important but not very explored worldwide. In Brazil, it's the contrary. In Brazil, we have lots of good polarimetrists. So the Brazilian Economic Society, let's talk about the readiness for GMT science. And I think we can say with some certainty that we are ready to use as best as possible this new facility, right? If you look at the last 10 years or 20 years, stimulated by the participation in GMT with the money and the efforts that were carried out, we have advances in astronomical instrumentation here at IAG, for instance. We have made these the new model for adaptive optics at SOAR, which is now working, which is SunPlus, for instance. System engineering, software development, detector systems, and also science outreach and training. It's going to be the talk of Eduardo soon. And for sure, we can say that we are internationally competitive. We have internationally competitive groups in the most important fields of astronomy these days. Galaxy evolution, stellar astrophysics, exoplanet, transient astronomy, cosmology, polarimetry too. So in the next 5 minutes or so, I'm going to give a few examples of science cases that Brazil can explore with GMT. But before I do that, I'd like just to point out to the younger generation here that GMT has a science book. It was issued in 2018. And as of now, the science book is being revised. So please stay tuned. Very soon is going to be, a new version is going to be published. And why it's so important? Because when GMT was conceived like 20 years ago, JWST didn't exist. Rubbing was not operational. AI assisted surveys in astronomy was immature. Now we have rubbing dominating the transient discovery. JWST has already transformed infrared astronomy. Roman is approaching launch. SKA is coming, and etc. So in the last 20 years, there has been so many advancements in astrophysics and so many facilities have matured that it's important to look at the science cases again and answer perhaps the question that Professor Elizabeth asked, what's going to be the synergy between GMT and these new facilities? So now I think I understand your situation a little bit. You said that you are using slides that you didn't do yourself. Now it's my case, right? I've been going to, I'll show you a few slides showing science cases sent to me by colleagues. But these are examples of science that could be done as of today if the instrument was ready, right? So one of these slides sent to me by Dr. Gilzo Montagut, sorry, probing environmental galaxy evolution with GMT. So what is established? Transition galaxies are a population that are very sensitive to the environment. So here you can see in this image here. In the top, you show morphologically disturbed systems that have undergone interactions and stuff. And in the bottom, you see more regular, but across different columns, you see in the local group, in the group, in a group, in a compact group, and in the field. So these transition galaxies are profoundly changed by their environment. The objective here would be to use GMT spectroscopy to identify the mechanisms that transform these transition galaxies in dense environments and measure the time scale of this transition. So how? What instruments are important for this project? GMAX is going to provide wide field optical multi-object spectroscopy, and the objective to answer this question, are the transition galaxies in dense environments older, more metal-rich, and quenched faster than the field? And using the GMTs in the infrared, the objective is a little different. Is there bulge growth, merger butte, the classical view, or secular, right? So this is very interesting. Going to a larger scale now, thanks to Professor Eduardo, who sent me this slide, the question here is to study galaxy clusters and dark matter in the GMT era. So he brought here two ideas that could be explored. The first one is the epoch of cluster assembly. So GMT spectroscopy will enable detailed studies of galaxy clusters close to the main epoch of cluster assembly. So the key goals here include galaxy evolution, quenching of star formation, cluster dynamics and mass assembly, and the baryon-dark matter connection. Using something that's very, very important is this wide field spectroscopy, using manifest with GMAX, as you've seen in the previous slide, in the previous talk. This can increase by a factor of many the field of view of the instrument when coupled with manifest. The other size case would be strong lensing in the high redshift universe. So we know that massive clusters act as gravitational telescopes, magnifying extremely faint background galaxies. So in this context, using lensing as a tool, GMT will combine spectroscopy, adaptive optics, and lensing to study galaxies during the epoch of reionization way back in the past, the first stages of galaxy formation, and resolved properties of lensed high G galaxies. So now bringing things closer, it's interesting to consider that many times when we think about bigger telescopes, we think about farther away, right? We're seeing further away because things get dimmer. But in the case of the solar system, it can mean smaller. So you have access to smaller objects that other telescopes would not see. So one of the science cases brought here by Professor Pedro Bernardinelli, which I think is sitting here. I hope I don't say anything wrong. So ICES in the solar system. So he brings this interesting case where small trans-Neptunian objects, TNOs, present a well-known color bimodality, right? And the few TNOs accessible from James Webb show three compositional groups, right? And here is the key. In small TNOs, the composition is thought to be primordial. And this seemed to me a very important point to stress, because being primordial, the GMT is going to open a new window to these small bodies, right? And actually be able to detect them and measure them. And the instrument here brought in this science case by Professor Pedro is GMT NIRS. Another case that he brought, which I found very interesting, is IFU mapping of comets and interstellar objects. So here's the JWST IFU mapping of Three-Eye Atlas, which is a very famous object, like 2 months ago. And the science case is very interesting. He says that cometary activity is driven by volatile materials. And this instrument, GMTs, will provide high-resolution maps of newly discovered objects from LSST. So here we see a very strong synergy between different facilities LSST discovering this small bodies in the solar system, and GMT following up with spectra. And the key point here, I think it's very interesting, is that activity beyond 20 AU from the Sun is still poorly understood. And the question is, how do comets become active at such distance, while objects that, like trans-Neptunian objects do not, right? So this is very interesting. And this is my last slide, going to now to stellar astrophysics. One of the key things that GCLEF is going to provide is very high resolution, like up to 100,000, with very, very, very high signal to noise. And this is going to allow us to study the heaviest elements, for instance, the lanthanides and actinides, for instance. So you really need really high resolution coupled with really high signal to noise, because these lines are very, very weak. So I think that's all. Thank you very much.
Thank you very much, Alex, for your talk. Question for Alex? We have time for one question. No?
Thank you. Thank you, Professor Alex. I have a question both for you and for Professor Daniel. It's a simple question. I would like to know about your personal views. When is the first light of GMT coming?
I think he has to, he's in a position to answer this much more properly than I am.
I've been instructed that the answer to that is in the 2030s.
Between 2030 and 2040, yes.
Thank you.
Okay.
Okay, so if there is no more question, we can discuss later in the coffee break. So thank Alex again. Thank you. And now I will present Professor Rafael Ribeiro here from l'IAG, and he's going to talk about recent developments in astronomical instrumentation at GMT Brazil office.
Cadê o seu cabinho? Só plugar aqui, né? Mas não.
Mas esse está plugado?
Esse está plugado aqui? Esse aqui. Ah, desplugado.
É porque para
deve que desligar os que usa aqui, né?
Sim, se você fizer. Agora já está ligado aqui.
Já vai. O quão próximo é, né? É assim mesmo?
Sim.
Ou ao contrário?
Assim, com essa coisinha apontando para o outro.
Pra fora, né?
É, ficou.
Deixa eu ver se tem uma plaquinha HDMI.
Não, não tem. Não tem. Não tá indo?
Deixa eu ver o que eu posso fazer. Eu vou pegar outro cabo.
Eu tenho um cabo aqui.
Eu tenho lá.
Você tem? Eu tenho aqui também. Sempre trago um de backup. Aqui.
Esse é HDMI?
Esse aqui.
Ah, tá bom. O outro adaptador.
Não, cabo, falei cabo, mas é adaptador. Menos das minhas aulas com ele, né? Não vai aparecer. Tá dizendo aqui que vai pegar, eu acho. Vou colocar.
Acho que foi.
Foi? Maravilha.
Já está tudo certo?
Tá tudo certo.
Okay, so let's begin.
Okay, everybody can hear me? Lights, please. Okay, good afternoon, everybody. My name is Rafael Ribeiro. I'm a professor here at the IAG, and today I'm going to talk about the recent development in astronomical instrumentation at GMT Brazil office. First of all, the outline is only two sets. The first of all is instrumentation at GMT Brazil office, in which we'll talk about what are our projects and our collaboration in the instrumental development of the GMT related projects as well. And most important, I think, that is the spin-offs of this group, in which is what are instrumentation that have been working, and also the founding of the Steiner Institute. So the first part, the governance of this group that was created by to coordinate the Brazil FAPESP efforts has the astronomical instrumentation the same horizontal level of importance in the governance. So since the beginning, we have put a lot of efforts into developing this part of the research here at the UAG. For those who are not familiar, the GMT Brazil, GMT FAPESP project started in the, not end of 2000, is incorrect. It started in December 2014, and the end date is August of 2027. So it was more than 10 years of project in which was completely funded by FAPESP. The host institution is here at the IAG, and the PI is Professor Laerte, and the researchers is Alex, Angela, Augusto, Claudia, and Flavio from Unicamp. And the management of all of this group is done by Diana and Pascoal. The creation of the GMT Brazil office is based on a research and development group to organize it and to participate in the development of GMT project and instrumentation in general. So the GMT-BRO has been developing the human and technical infrastructure necessary for Brazilian participation in astronomical instrumentation. So it was an integration between academic and professional engineering, in which we have the creation of multidisciplinary teams. That is this is the logo, and here's the website. Important to mention that it's between academia and professional engineering as well. So since the beginning of the project, we have included engineers from several of expertise, military, meteorology, and aerospatial, since there are being a lot of combination of expertise between the needs of astronomical instrumentation. Here's a very dense slide here, in which shows below the astronomical instrumentation, which are the area in which work for the instrumentations at the GMT. So we split into astronomy, system engineering, optical engineering, optical mechanical and mechanical engineering, software and control, electrical and electronics, and simulations as well. I'm not going to go into details, but all of these activities has been developed during these 10 years of project. The telescope design, it was very well described by Dan, so I'm going to skip it. For those who are more interested to go deep into the astronomical instrumentation behind the GMT, go to these SPIE proceedings. That was back in 2024, and in a few weeks we are going to release another one, which is updated of the science instrumentation for the Giant Telescope. And now go into the focus of the instrumentation suite, that is instrumentation stations. The GMT has three instrumentation stations. The first of all is what we call the narrow field station, that is manned by the fold port. Is accessed by the tertiary mirror. So the tertiary mirror is here, and this setup can be able to feed 3 instruments or more. Below it is the Gregorian focus. There is 3 wide field stations that can go to the 20 Archimedes field of view. So it's the DG and the director narrow and wide field as well. So it is this bay. And what we call the gravity invariant station that is close, that is this part here, at the azimuth platform, that is very stable flexure instrument. For instance, the G-clef that is located here. Now I will return to each of these ports and show the instrumentation in which Brazil has collaboration. So the first one is the fold port. Brazil has involved in 2 of the instruments. Actually, it's not a instrument, this one here is a test camera, and the GMAGL-X, which was being discussed here. The first one is the adaptive optics test camera. That is the PI's Rick Demers. It's a correct preliminary design, and actually is an instrument to test the adaptive optics of the telescope. So it's comprised of several channels. So it's a diffraction limited near-infrared camera with a 10 arcsecond diameter field of view. We just addressed it now in March 2026. The PDR calls for a preliminary design review. So it was approved and we are in the final design. And the participation in Brazil, we have been involved since 2023 at least. We have worked on the main mechanical layout, the optical layout, and several of the finite element analysis as well. So it was more than 7,000 of engineering time. When I call here engineering time, it means there are our fellowships and all the engineers which is involved. So in a range of 3 to 4 years, it was more than 7,000 engineering hours. And we working on several parts, the mechanical, optics, and software as well. It's not included here, but software was relevant. And the partners is the GMT, Telos, that was a company at the United States, GMT, and the Steiner Institute, which I'll provide you soon. The GMAG is we just started the collaboration. So we started the collaboration. It's as Dan mentioned, is extreme AO system for visible and infrared for high contrast image and spectroscopy. So we have the PDR February 2024, and we are started a collaboration here at the University of São Paulo with the design of some light stop for a wavefront sensor camera. We just started right now in the mechanical and optics. Now for the wide field. So for the wide field in the de Gregorian platform is one of the platform which we have more collaboration. 3 of the 3 instruments we are involved. So GMAX, CONCAN, and Manifest. GMAX is one of the most important projects that we have been working. You can see that, well, it's not the next slide, but we've been involved since 2015, so 1 year after we started the GMT FAPESP. The PI is Dan Fabricant from Harvard-Smithsonian. So the current phase we are in standby, but the next is the final design phase, which we expect to appear to have in the next few months. And it's a wide field and high throughput, low to medium spectral resolution, which operates very down the blue through 330 nanometers to 1,000 nanometers. And the contribution of Brazil, as I mentioned, we have involved in several of these phases. Back to the time that the PI was there deployed from Texas University, we have been involved in the conceptual design, post-conceptual design, preliminary phase 1, and preliminary phase, which was hosted by Center for Astrophysics of our colleagues of Harvard. We were responsible / working with the team in order to provide the optical design, some principal mechanisms, and the design of the test stand. Test stand is a parallel project. It's a separate project of GMAX that is designed the structure to test the GMAX. And we have more than 15,000 engineer hours working in this project from the preliminary design since 2021. So it was a lot of efforts. The next project is a CONCAN. CONCAN actually is not an instrument, it's a commissioned camera, but we are exploring capabilities to turn this instrument into this facility into an instrument by itself, by including Fabry-Perot and polarimetric capabilities. The PI is Jaffe crane from Carnegie Observatories. Right now we are in the final design. It's a real reflective visible image camera, and there's a lot of efforts for public outreach functions and scientific research opportunities as well. So in the end of 2025, sorry for that, it was approved. The PDR was approved and we were involved in it. And Here's the Brazilian contribution. So we're working on mechanical, software, and electrical engineer. Here's the design of the upper and bottom IMF mechanical design, completely done here in Brazil by our team, together with the Jaffe teams. So we have more than 6K hours, engineering hours, since the PD, that is back to 2024. The other project, the other instrument is Manifest with the PI of John Lawrence from Macquarie. We are in standby, and the next phase is preliminary design. We just have this conceptual design approved back to the last year. And the Manifest, for those who don't know, is a facility robotic fiber positioning system in which we'll feed, for instance, GMAX in order to address all the 20 arc-minus field of view, the complete field of view of the GMT. Our participation in Brazil was since the pre-conceptual design, 2020. We work in system engineering, optics, and mechanical. We were and we are responsible for the complete set of what I call the filter box design. Filter box is a system in which we will integrate with the GCLEF in order to provide some filters capabilities. It was more than 15 kilo engineering hours applied since back to 2020 in this project. The partnership is with Macquarie University. And the last one is the gravity inverted station, which is GCLEF. And GCLEF, we have the PI is Andrew Stewart from SAO, Smithsonian Astrophysical Observatory. We are in the phase of fabrication, actually. It's a visible Kelly spectrograph with a high resolution, up to 100,000, and fiber fed with high precision radial velocity capabilities. Here you show the instrument, but what is the path in order to go to the tertiary mirror to grab the light. And here's the cross section of the instrument. And our participation here was in two fronts. The first of one was development and the prototype of the exposure meter. Actually was done by one of the students here at the IAG. Exposure meter is one small spectrograph, which is inside the spectrograph in order to calculate to make the correction of baryonic calculations. And another very important project, which is actually a parallel project of a past project, is the ASTROCOM, led by Flavio Cruz. That is the optical frequency comb for astronomy. This is a technology in which we use to calibrate high-resolution spectrographs. So it's a brand new technology that has been incorporated into astronomy, and it provides a very stable calibration for high-resolution spectrographs. And not instrumentation, but rather GMT as well by itself. The telescope will have been involved in few areas. System engineer, which is one of our workhorse engineering efforts for the IG, which has been more than 10,000 engineering hours in the system engineering process and all of the activity that is done under this subject. And we are working as well in quality assurance process for the GMT. And for software, we have two fronts, the observatory control system and the GMT device control system, which is directly related to GMT as well. It's not instrumentation, but well, it's related to the telescope by itself. And here is a deployment timeline of the GMT, in which shows what is the segments and what is the instrument and what is the phase that will be deployed along the time. So there's no time here for a reason. And I would like to highlight the participation in Brazil. So we are very highly involved in several of the fronts in Brazilian in GMT instrumentation. And as you may expect, the partnership is also very strong. So we have a close relationship and partnership with the GMT telescope, of course, with Harvard, AEO from Macquarie, Carnegie Institute, of course our host, that is University of São Paulo and IAG, the University Instituto de Física de São Carlos, Unicamp, Mauá, and Univap. So this is our picture of what we have been done here. Now the spin-offs, which I mentioned that is quite important for us. This is another view of the project that is based on the GMT project and what is the area and in which of the projects we are involved. And I included here two more, the Sun Plus and the near infrared camera, which is not GMT related project, but rather is a instrumentation and development in our institution that has been like heritage from what would have been done. So the first one is Sun Plus. Sun Plus is the SOAR adaptive module, is an upgrade of the SOAR adaptive module. It's a modernization of the original SAN, and it has been commissioned in 2024. It's successfully commissioned, so it was completely designed here at the University of São Paulo with our team here at the IAG. And here are a few of the news on some website, and it shows that the Brazilian delivers the first adaptive optics developed in Brazil, and we are proud to make part of it. And the other one is NIRCam. It's a development of a near-infrared camera. Actually, it's one of the brand new part of the instrumentation in Brazil. It's a very important part in the instrumentation side, the development of cameras. We are not being involved in any of the instrumentation, but we see that it's important for our team here in University of São Paulo to develop it. So we are putting some efforts into this development of a general near-infrared camera. And most important is the Laboratório de Ótica, what is the optics lab that has been developed for this project as well, in order to give us the possibility to assemble, integrate, and test of optronics and optomechanical devices. So it's an ongoing and in current development laboratory in order to create more capabilities, in order to base all of our efforts in instrumentation to be done here at the IAG as much as we can. And important to say as well the schedule of the project and what is in Brazil our participation. So the participation was through the GMT FAPESP in 2015, and we did the project we went in 2027, but the project will go to 2035, 20 and more. So what we are going to do? So we have been developed all of this human resource, infrastructure. So what was our idea in order to keep this going? So we are working on to have the GMT FAPESP, what we call the GMT FAPESP 2. So we are looking for funds. We are proposing some different approach in order to keep going with the instrumentation side. And the GMT BRO is a no official entity, is a group here at the IAG. So if there's no fund, only the professors will be involved. And therefore we decided to have an alternative in order to keep this heritage, to keep the human resource and infrastructure working for the instrumentation at the IAG. And after a long discussion, we decided that the best approach was to create what we call the Professor John Steiner Institute of Instrumentation and Data Science, in which is called the Steiner Institute. Actually, it's a trademark, it's true. And I'm proud to say that is the one spin-off of our Department of Astronomy. It is the foundation of this institute. It's a non-profit private organization. We started the operation in 2022. We have almost 40 professionals involved in our activity, which were from the GMT BRO, so it's a natural heritage from this astronomical academic group into the more formal group, with the main goals to support this GMT BRO group activity and operation, to promote the autonomy and long-term sustainability for the instrumentation group, managing institutional and project resources, establish strategic partnership, development instrumentation and data science for sure, and of course to contribute to the scientific and technological development in Brazil. And for those who are familiar, Steiner is to honor our Professor João Steiner, which was the head of the GMT project back in 2014. And as expected, all of the works, all of the activity that was being done by GMT BRO is gradually moved to the Steiner Institute. So all of this project now has Steiner Institute involved as well. with a formal agreement with the GMT and also with Harvard, Macquarie, and Carnegie. And we are working on across 9 technical operation fronts within the GMT. So it was very robust. So we say that we were born in a very rich place, and the goal is to keep going, even if a PESP doesn't give us fund enough, or if we can't find any public resource. So as I mentioned, is a private non-profit organization with no relationship with the FAPESP, University of São Paulo, and so on, and IAG as well, but we have a collaboration with them, of course. And Steiner Institute aims to go ahead, I mean, not ahead, but more than what GMT can propose. So we working on different instrumentation for as well. So since that we are working together with our partnership, there are a lot of collaboration that can arise of this approach. So for instance, the VA spec is a spectrograph that is being done by Carnegie and SAO. They invite us to develop a few parts of the instrument. We have been contacted as well by our colleagues at Mackenzie in order to develop the spectrograph module for the ground solar space, from a ground-based solar observatory as well. We working on SunPlus, so not only IAG, but Steiner Institute as well, working on SunPlus. And we've been working on customized atmospheric dispersion corrector for AO systems. And since that our goal is to keep the funding from different not public, but from different sources that is not public, we expand our capabilities as well. And one of the ways that expanded is that we, at the Steiner Institute, we acquired the intellectual property of the bomb shutters. That was a very big movement into the shutters. For those who are not familiar, mechanical shutters is a mechanical device that is actually in all of the cameras, spectrograph and photometric cameras and so on. And the company called Bomb Shutter from Germany, in our environment, is one of the best of the world. So they are online in more than 30 years, providing shutters for specific astronomical instrumentation projects. And they decided to close their activity, and we were selected as their competent successor here in Brazil. So we acquired all of the property of the intellectual property of the Bomb Shutter, and in order to make it happen, the Steiner Institute created a subsidiary in order to commercialize the shutters. So now we not only can design our own shutters based on their technology and on the upgrade of what we can do better, because, well, the Germany can do very good shutters, but there was a lot of obsolete items in which our team is working in order to make it happen. And the idea is to have this opportunity and alternative to have this commercial side of the Steiner Institute as well, in order to provide to the community the best shutters as possible, including our community, our astronomical Brazilian community as well. So it's a proud to say that we have this in our portfolio. And thank you, that's all.
Thank you very much, Rafael, for your talk. We are open for questions. Okay. I'll start here because of geographical.
Just a comment about
For
the
sure.
schedule. The telescope won't all be finished all at once. So whatever timeline you want to believe, things will come gradually. And so it's important to remember that the natural light things will come first, and the adaptive optics things will come second.
Yep.
So as you think about what you might do with the telescope, you'll need to be more patient if you're thinking of adaptive optics things, but there'll be many, many things to do before that.
Yeah, appreciate it. Great.
I'm wondering, we have the design of the telescope, the grand design, and how does this design relate to the final product we obtain like everything that's on the first design is on the final product, or does the design have a life on its own and design is susceptible to changes?
You mean the design of the telescope by itself?
Yes.
I don't think that the design of the telescope will change. It will like have a cascade of changes, because the telescope is the first thing that will see the light. So all of the instruments and the instrumentation, the facilities, is based on this design. So the first thing that we do in a such large development is to freeze the design, the prescription data of the telescope by itself. So it's pretty fixed. So it will not change, not at all.
So the changes occur on like specific instruments.
Yes, the instrument will use the prescription data of the telescope in order to be designed.
Yes.
So it's the first input.
Okay. Thank you.
Appreciate it.
Okay. Do we have more questions? Yeah.
It's just a curiosity. It's because I didn't know about the Steiner Institute. I would like to ask how this idea came to the founders. Could you talk just a little bit?
For sure. The best answer is to see this graph here. So the participation of the Brazilian side founded by FAPESP will end. The project has an end, so the funding will end as well. So after it, we will simply grab our things and go out, and leave the project. So in order to not lose all the heritage, the personnel, the infrastructure, the management aspect of how instrumentation, of development of high complex instrumentation is done, we decided to create the Steiner Institute. Of course, that was not a straightforward decision. There is a lot of trade-off with thoughts, and we went to different situations, for instance, centers or public outreach and so on. So we decided to create this non-profit private organization. So it was the best in order to keep going.
Okay, more questions, Rafael? No? Okay, we can talk to him during the coffee break.
For sure.
Thanks, Rafael, again. Thank you. And we will move on to our last presentation of today, that is going to be given by Professor Eduardo Cipriano from here, the IAG. And Eduardo is going to talk about GMT and the expansion of science outreach in Brazil. Great. Thank you, Eduardo.
Well, thank you very much for the invitation. Posso começar?
Tá bom. Você vai passar o slide aqui mesmo?
Yes.
Tá funcionando isso?
So, I'm going to talk about the initiatives of the GMT Brazil office regarding both science outreach and education. So the science outreach is led by me, and education by Professor Liz Figueiredo Cipriano, which also gave me her slides, so I will suffer the same as Alex suffered before. So it was funny because GMT computes all the money from the partners as private money, but our private money is 100% public, which comes from FAPESP. And as we are funded by the people of Brazil, we feel obliged to give back as much as possible, even right now before the telescope is built. So that's why we are investing heavily in science outreach. So that's this whole cycle of doing research and trying to make it understandable to the public, which creates people that we want, new people that we want enter academia and do research. And it fosters the use of public resources as well, which on this sense will keep science research alive. Okay, so we are part of this process. Okay, but fortunately, in the last years, since the pandemics, a lot of people realize how important outreach is. So a lot of our students probably are doing lots of outreach on social media, lots of influencers, and therefore the space is a bit crowded. But we have our own space on that, and this is our manifesto. We don't play the game in the same space as most of those influencers. For instance, we refuse a lot the sensationalism that always follows research, like JWST is there, find some red galaxies, high redshift, cosmology is broken, everything is broken, you have to rebuild everything. So we don't do that. So we have the name of our institutions, which are some of the most well-regarded in Brazil, and therefore we do very serious sciences. And mostly, we always try to show the public that we do have the knowledge in those areas here in the country. Because people usually often see like foreign scientists talking about all the latest breakthroughs, and they don't realize sometimes that we do have this knowledge and this know-how in Brazil. So one of the main goals of this our outreach is to highlight Brazilian science and engineers. And of course, by doing that, we aim to inspire future generations, youngsters that want to become scientists. We want to empower these people, say, well, if this guy, which has the same looks that you have, is a professor at the university, you can be in the future, okay? And connecting the whole society, not with science, but as well with the steps of the Giant project. So the first thing we did is to professionalize science communications, because we are very aware that as scientists, we are not particularly gifted to communicate in social media and those kind of spaces, especially because we are 30, 40 plus years old, and we don't have the skills that most people see. So we let communication for the professionals. And we have a strong collaboration with the University of Vale do Paraíba in São José dos Campos, Univap, especially with the team of TV Univap. So this is Felipe Soriano. He's the coordinator of the communication group. So this is Amanda Cassis, that is the science journalist that do all the writes everything that goes to internet, checks with me, checks with them, and our interns that do the video collaborations. And Amanda is as well is the voice of GMT outreach group in all our videos. Okay, so there's a strong collaboration between us, the scientific team, and the communications teams. Not easy. They would want to be much more expressive than we allow them. And of course, sometimes we propose corrections that makes everything a little more boring. And then they make things very exciting and very engaging. So the first contribution we have is this series, which is called The Fascínio do Universo, The Allure of the Universe, which is a mini-series of 2 seasons, which are on YouTube, regarding astronomical concepts. So it's like 8-minute videos with a single astronomical concept where we interview a Brazilian scientist or specialist in that particular area. And we have narrations by Amanda Cassis, animations, archival images, and always in the end, we try to figure out how GMT will be able to contribute in this particular area. So it started just before pandemics, had to stop, and then we start publishing this in 2020, and up to 2024, 19 episodes. We have on total more than 200,000 views, both in our channel and the university channel, which always reproduce that. So after we kind of exhausted, we start going for 2 deep concepts. We start thinking that one particularity of our participation on GMT that no other influencer, scientific influencer, talks about on the internet is about instrumentation. So we thought about this new series called Shooting for the Stars, or Mirando as Estrelas, which focus on instrumentation. We aim to talk about not only about with kids that like science, but people that likes technology as well. Which sometimes there is an intersection between those groups, but sometimes don't. So we are trying to talk with people that love technology. And therefore, we change a little bit. The language is more youthful. Now the narrator appears, Amanda. You can see Amanda now in the videos. And then we are talking about all the projects that there is Brazilian participation. A lot of them regarding GMT, but some regarding all other telescopes. So the cubes that Beatriz is doing, for instance, and others. The focus is on the instruments. So we have also short episodes and teasers, contents of social media, development of 360 degrees videos, such as the one I'm going to show, if everything is all right. It's a work in progress. The labels are not there yet, but this is G-Max. So this is where you put the slit mask, and the other slit masks which are not over there. And we are going to go through the whole instrument. So this is very professional. That's not something that we can do at home. Okay? It took a lot of effort. Rafael is a consultant here. They use the 3D models of the actual instrumentation. You can see both channels, the blue and red channels. The change in the grating angle. I don't know if that looks simple or not for you guys, but it is so hard to make. Okay? And there's a lot of CPU time as well. So this is our G-Max. And this is the kind of content we are trying to include on this new series. Okay? So our future directions are keep investing on the social media with astronomical news and history of astronomy, doing documentaries about the Allure of the Universe series, and they are developing 3D videos for shows where we can use the 3D glasses, stuff like that. And we are not like the most famous outreach people on the internet, but we have a solid base of viewers and views in our videos, which are quite in line with our manifesto and our purpose. So I move now for education. So in the education activities, they are not 100% of the GMT BRO, although it's coordinated by Liz, which is part of the organization. But we talk about GMT, but not all the activities I'm going to talk about has been funded by the GMT BRO. But yeah, of course that happened, and it's a spam, of course, and yeah. But over the years, GMT contributed a lot with this institute through what we called FAPESP RTI, which is a technical reserve, institutional technical reserve. So if USP is, and the Institute is contributing to these education activities is part of like a counterpart from the FAPESP RTI, which has been a lot of money, very important for our institutions. So the activities, there are three main ones. The one that GMT is more involved with, GMT BRO, is the Astronomy for Teachers. And the Cecilia project is another one that goes for public schools. And Astrominas, which is an initiative focused on the inclusion of women in astronomy and other STEAM areas. So let's start with Astronomy for Teachers. It's a very strategic because you teach one person, and this person will reproduce this knowledge for lots of other people. So it's very strategic. And this course runs since 2011. So it's also a John Steiner initiative. And it's been fully online since 2021, which allowed us to reach regions in Brazil we couldn't do before. It's largest, so it's not that a small course. It's all online on Moodle with activities, tutor, etc. And as all those activities, we put a lot of emphasis on the hands-on and experiments. It's just not talking, but doing things that demonstrate the concepts we are trying to pass to individuals. Okay, so we do it every year. 120 spots for teachers, and so that's it. That's the latest one we had. So this has more of a contribution, financial contribution from the GMT BRO. So second is Projeto Cecilia, named after Cecilia Payne, the famous astrophysicist. There's two sides of it, online and in person. This is the online version, which shows how we can cover a lot of Brazil, including one school in Peru that deals with the Portuguese language to be part of Cecilia. So this is a series of activities that you do every day between small lectures and local experiments, and are mediated by our tutors. And from 2 weeks, we interact with those schools, and in the end, they have to do a poster like that shows what they learned, that they like it most. And we have online lectures and workshops, daily follow-ups and discussions, and about the content, and also careers in science. So the inspirational part is right there. Okay, so it's also annual cycles, 60 schools per year, which have 2,400 students. And also, when the students learn, the teachers learn at the same time, and the reproduction cycle goes on and on and on. And the other one is the in person. So this is the map of the greater São Paulo. So we put our students here in a van, and we drive for 2 hours, because always in every distribution there's much more area near the edges than in the center. Okay, it's a mathematical fact. So it's always very far away, and we only attend public schools, which are found more commonly in the outskirts of the city, what we commonly call periferia. So this is the Projeto Cecilia. So we are talking about this beautiful telescope here. Here he is explaining, but it's the minority of the activities is someone explaining to people. Most of the activities is someone looking to a telescope, playing with an experiment and things like that. And our crew only talks in the beginning of the activity, and they train some of the top students, and then our people, which you wear this black jacket here, they went outside, and they allowed the students they train to talk to the other students. Like they train ensino médio, how I call that in English? High school students. and they talk to fundamental, I don't know what that in English is. Elementary school, thank you very much. And their colleagues, they pay a lot of more attention when they see their older colleagues to talk to them. So this is a lot of fun, and I've been in some of those visits. You come back here completely exhausted and 100% happy. Okay? So, and the last thing I'm going to talk is Astrominas, which is a play in words for who among us don't speak Portuguese, as Minas is an informal way to say women, young women. Okay? And so all the lectures are given by other women, our researchers. We have lots of very successful female researchers in our area and the correlated area, so that's not a problem at all. And that's to encourage girls and young women to pursue careers in astronomy and other areas of STEAM, and presents role models, so other women that has been very successful in academia. And of course, we teach the astronomy that is what we do. Okay, so this is the cycle of this activity, and that's it for today. Thank you very much.
Thank you very much, Eduardo, for this wonderful talk. Do we have questions? Do we want coffee?
Yes.
We will thank Eduardo again, and we will discuss with him during the coffee break, and we will thank everyone, and of course, thanks all the speakers from today. Thank you very much.